this meeting mostly because we're interested in diversity, some aspect or another, or how that diversity came to be. How did there get to be so many species on this planet, and how do they coexist with each other? We have a couple examples from like the Caribbean anoles or Darwin's finches that have helped us learn how species can specialize and coexist, whether by diversifying on different foods that they eat or making different ecomorphs that live in different habitats. But we often struggle to apply these away from these fragmented, isolated systems into more continental systems where there's more admixture between species. We also struggle sometimes to know how specialization can evolve itself, how do lineages get the fuel they need to then keep on specializing, if that's what they're doing. A couple hypotheses that have recently been proposed are ideas of oscillation, that lineages might go back and forth between different sequential phases of niche breadth and then niche specialization, and niche breadth and specialization. Or there's the idea of musical chairs, that they need to find a new empty chair that they can sit in, a new host or a new niche of some sort that they can specialize in. Just a couple of years ago, a study of some butterflies found that as the diversity of the host plants the butterfly is using became more and more specialized, fewer and fewer taxon diversity, the diversification rate of those families and of the species increased. So it seems like these are options that could be there to help us learn how specialization arose, but we don't have a lot of empirical data to help us understand how these are coming out. So the sort of organisms that I love to work with are called robber flies. They're some of the coolest animals that many of you have probably never heard of, but they're really cool. They're predator insects. They're one of the most diverse species of insects. Or diverse groups. There's about 7,000 species. They're worldwide. Everywhere you can find terrestrial habitats, you'll find robber flies. They are ambush predators that fly out, catch other insects in midair, and then bring them back, stab them, inject paralytic venom, and then suck out their guts. They come in lots of different shapes. Here's a bee mimic. In sizes, they can go all the way from 3 millimeters that'll eat tiny little noceums or gnats, to great big, giant, honking, 50 millimeter long flies that can bring down any other insect practically. The robber flies that I study especially are these fairly drab, smallish looking ones. They're only about 10 millimeters long. Here's one eating a beetle in the sand of this river wash at the Santa Ana River in Southern California. Like I said, most of them tend to be this fairly gray, indescript color, but there's a lot of surprising diversity when you start to look at them more closely. This is just, if you compare the phallus, look at the tips of it, you can see there's lots of different variety and different flanges coming off the top or the bottom, the curvature. These are all different species that we find in Lysopogon when you start to dissect them and look at that cryptic diversity. So I've been interested, why are there so many species in Lysopogon? There's about 120 species worldwide. Half of them are in the Arctic. I'm working on revising these groups right now. And one of the things you notice with them is that they chase spring. They're usually the first species of robber fly to emerge at any given site in the range. Right after the flowers start to bloom, they'll start to come out once there's enough prey that you can support a predator fly. They're also the farthest north of any robber fly. They go all the way up to the Arctic Ocean. So they seem to do well with cold there. But we find that there's multiple species coexisting at the same sites, which is sometimes frustrating and surprising when you're trying to understand how to reconcile that with the idea of niche divergence and how do we have coexisting species with overlapping ecologies. So to study this question, assembled a data set of all the localities for North American Lysopogon. This is primarily from museum data. It's also from collecting. I've gone around collecting about 3/4 of these species myself. And it's been a lot of work, but it's been a lot of fun traveling around catching all these flies. Next, we also need to know how they're related to each other. So I had to catch amount of samples in large part because most of them hadn't been collected for decades or almost a century, and so they weren't usable for DNA analysis. So being able to construct a species tree for these species using 4 loci so far, 1 mitochondria, 3 nuclear. And by and large, these species groups are fairly congruent with what we were finding with morphology analysis 10, 15 years ago. So that helps me feel like we're actually getting something real here. What do we see when we start to look at these patterns? First, we see that different species groups have different biogeographic histories. There's some species groups, like this light blue group, that are very broadly distributed. They go all the way over into Asia, all the way to Finland, actually. These three groups all have species that go into Asia and Europe. Other species groups are more focused and have expanded in different areas. Some species are very widespread. An individual species can span several time zones, or hundreds of thousands of miles, and other species are very localized endemic groups. And you'll notice that these are also both spreads throughout the tree, where the endemics and the widespreads can be found in many different groups. This pattern also shows up when you start to look at climatological data. Some species have very broad ranges of precipitation and temperature, and other ones are very focused. This isn't just a matter of sampling, these are actually what they might have the same number of flies, same number of collecting events, but they are focused in different spots. When we look at this with some phylogenetic perspective, we start to see there is a lot of overlap. There are some patterns we start to see with how different groups have different variances and different means for what type of climates they're preferring. So I wanted to analyze this. I looked at how the niche breadth, here estimated using the covariances of the temperature and precipitation data for each species, corresponds with the diversification rate of each species. And we can see that similar to the study we saw with the caterpillars at the beginning, there is an overall declining rate where as the niche breadth becomes narrower and narrower, as they have less diversity in what they're doing, we also find that they're able to specialize and get more species. But I want to throw out a word of caution that we need to remember that species distribution models and climate values are not in and of themselves niches. We often use them as an proxy. We like to take our localities, we plot them on a map, we extract out the 19 bioclim variables, and we call that the niche, and then we try to bash our head with multivariate statistics and figure out how these species are different from each other. That doesn't always work. Sometimes it works, sometimes it doesn't work. And it can be useful to look at things from a different perspective sometimes. We've seen this meme floating around Facebook in recent years. Sometimes we need to look at the same data from a different perspective, and we can start to see how it is actually true in another sense. So what does the fly see that looks at these localities? Well, the fly sees these at different times, because the flies down at the base of the mountain are coming out at different times than the flies at the top of the mountain. And so when they see what's coming out, they're seeing spring. They just see the same thing all the way up the mountain. You can track where when the sedges and irises bloom going up the mountain, you find that's when the flies are coming out. And so this niche might actually be more narrow than the broad smear that we initially thought it was by looking at just year-round means. Similarly, a recent example I just found last week, these three species can all be found coexisting on beach dunes in Central California. They're not sister species to each other. And so how are they coexisting? How are they often they have perfectly overlapping ranges on the exact same county of California and beaches that complement the exact same hills you can walk around there. Turns out when I plotted the emerging states for each one, they've got really good separation in phenology. They're coming out at different times. This is all the known specimens for these three species in the log basis here. So these three species, even though they share the exact same physical locality, and if you plotted them with the bioclim variables, you would see the exact same overlapping niche that way. They actually they see the niche differently from each other, and that's one which they're able to coexist. With robber flies, another dimension that they've been able to add is the dimension of perching in the microhabitat. Within a given spot, they can perch, different groups of perch in very different spots. The sand might have one species, the rocks might have a different species, the plants might have another species, the logs might have a different species. All these even within the same genus, within the Arthropods, for instance. Some are rocks, some are sand, there's others that are lava creatures. This might reduce prey competition by providing you slightly different vantage points to see who's flying in front of them that they can catch. And since we know that robberflies are cannibalistic, it can also potentially reduce intergroup predation amongst each other. So I think that we're seeing that these robberflies have a whole toolbox that they're being able to use to diversify. We've got, yes, we see that there's the history, the stochastic history of biogeography that's helping them split and through vicariance, but also we've got the climate tolerances, we've got the micro-niche, we have morphological differences, and we have different seasonal phenologies that are splitting the species. Some interesting things that will help us pin these down in the future more are looking at, are these perch differences between rocks and logs and sand, are they accumulating faster, slower than the climate differences amongst coexisting species? Do the polymorphisms we see with different colors or phenology, do those correlate with species interactions between coexisting species, for instance? And what mechanisms are actually driving the character displacement here? Is it competition? Is it intergroup predation? Is it sexual selection? And of course, how the larvae matter is important. Those are the phases of life that are actually seeing the habitat for the full year instead of just the 2 or 3 weeks that the adults emerge. Unfortunately, we know virtually nothing about larvae on BV, so that is a long down the road prospect for us to look into. So I'd like to thank you all, thank the funding agencies and the many people who opened their homes for me on the collecting trips, and I'll take any questions.
What traits do you think might be under sexual selection?
So I often think that they have different colored mustaches, white or black mustaches that usually are different between species that coexist at the same spot. And when you see them interact with each other, they often go face to face, and so I guess that they might be using that to help tell each other apart. And the genitalia, of course.
Yeah,
a broad diversity of genitalia, those are
right.
definitely under some sexual selection,
Right.
I guess.
This is tangential, but are they ever pollinators?
Not on purpose. You find them perching on flowers sometimes, but usually they'll eat the bees that are pollinating or other things.
I think I saw one in one of our stem plants, so that's nice.
They like to use them as perches. They use people as perches too. Sit under